Well, hello again. Let's talk about simple harmonic motion again, this time energy, damping, and resonance. So here again I have a simple harmonic system, a mass on a spring, mass M, spring constant K. If I stretch this spring some more through some distance x, we already know from earlier in the semester it gains some potential energy. The system gains a potential energy 1/2 kx squared. So that is the potential energy due to stretching the spring. If I stretch it to some maximum x, that maximum x is called the amplitude. That's the amplitude. So suppose I stretch this out to here and just let go so that this oscillates back and forth. The mass goes back and forth like this. At the maximum amplitude here, V is 0. So at that point, the system has 0 kinetic energy. So at maximum amplitude, the potential energy is 1/2 Ka squared. But that's the total energy because there V equals 0, so this is E total. Anywhere in between, say at this x, where the system does have a velocity, the mass might be going that way or it might be going that way, the system has some energy 1/2 mv squared plus 1/2 kx squared. It has a potential energy plus a kinetic energy, but that always has to equal this total energy 1/2 Ka squared. So I could, for example, use conservation of energy here to solve for V as a function of x. Notice the halves cancel. I could now take the kx squared over here, put it with the a squared. I get Ka squared minus kx squared equals mv squared. Factor out the k, divide by m, I get k over m. A squared minus x squared is v squared, or v is the square root of all that. V is square root of k over m, a squared minus x squared. And that's just an example of using what we know about energy, potential energy of a mass on a spring of a simple harmonic system, 1/2 kx squared, and adding to that understanding that the total energy is this 1/2 Ka squared. Now I'm not going to do an example of it, but I might also have used, for example, the knowledge that here at x equals 0, there'd be no potential energy, but at this location the mass has its maximum velocity. So the kinetic energy would be 1/2 mv max squared, and that would be the total energy. And I could work with that, for example. So that is just an example of use of energy in a simple harmonic system. Now I want to move on and talk about damping. So damping refers to effects of friction in a simple harmonic system. So suppose I have a system with, like we've been talking about, with no friction. So no, I'm going to say no damping now. And that means no friction or no energy loss. So that's the case we've been, without realizing it, that we've been talking about. So in that case, I could, for example, think about the following. I could have a mass on a spring like this, and I could, for example, push it up. So maybe this is the equilibrium position. This is x equals 0. This is A. Now push this up and release it so that it oscillates up and down like this. And I could graph, as a function of time, the behavior of this mass as it goes up and down between A here and minus A, where this is the X. This is its position up and down X. So if I push it up and release it, this graph would look like this. This is A cosine omega t we learned. And it was just, if there were no friction, no energy loss at all, we just do this forever, going between A and minus A. But there's going to be some friction. Suppose we now allow for friction. So let's have what we call damping. But now we're going to deal with, I should have said, under damping. That's our first case of damping. Under damping is oscillations of decreasing amplitude due to friction. So let me sketch it again. Here's our x equals 0. This is A. Down here is minus A. Mass is going to oscillate. I'm going to push it up and release it. I'm going to do a graph. But now I'm going to assume that, so here's A, here's minus A. Now I'm going to assume there is friction. So as this mass goes up and down, there's some energy loss due to various cases. It could just be lost due to the air around it, due to friction in the spring. So maybe, so as this oscillates, instead of going between A and minus A, it doesn't quite make it all the way back up. And the oscillations decrease like this. So this is time again. So now, the amplitude of the oscillations decreases. So underdamping refers to oscillations of decreasing amplitude due to friction. And that's really the normal case. That just means that this mass slowly, its amplitude slowly decreases. So for example, if this were a mass on a horizontal surface, you might stretch it out and let it go. It could be friction with the surface that slow it down. Now there's a special case we deal with called critically damped. What if there's a lot of friction? So here is my spring again. I'm going to push it up. This is x equals 0. This is A minus A. But now maybe I'll put this in a beaker of lightweight fluid. Maybe something like ethyl alcohol or something. So that there's quite a lot of friction as this oscillates up and down. If I choose my friction just right, I can keep this from oscillating at all. So here's time. Here's the amplitude. So this is A minus A. This is the x-axis again. And what you you can choose the friction so that you push this up and release it, and it just comes right back down again and doesn't oscillate. And so this graph would look like this. Critically damped is when you choose your friction so that this comes back to 0 in the fastest possible time without oscillating. So this is when you have the oscillation, no, sorry, it doesn't oscillate. The simple harmonic system returns to zero in the fastest time without oscillating. So the simple harmonic system returns to equilibrium. Let's call it equilibrium instead of zero. In fastest possible time without oscillating. There's actually a special case of this where it can oscillate one time and go underneath and restore it. So that's when you've very carefully chosen this friction. There's any other case, when there's more friction than that, this will return to equilibrium even slower, more slowly. So suppose instead of water, or suppose you put this in honey. So this would take a really, really long time, and that's called overdamped. So now, suppose I put this in the jar, I don't know why I put the jar around the graph, of something like honey. So maybe in your notes, call this water, just to give you some idea, and this is honey. So now this will take a really, really long time to return to equilibrium. So you got to graph something like this. So the system returns to equilibrium slowly, very slowly, because of excessive friction. System returns to equilibrium slowly without oscillating due to excessive friction. That's overdamping. So this looks contrived, but these cases actually occur. Well, maybe not really with honey, but for example, the shocks in your car. Shocks in your car have springs in them, but you also want to dampen the oscillations in your car. When your car goes over a bump, if your car keeps oscillating up and down, it means you need shocks. You want the shocks in your car to return your car to equilibrium quickly, but not too so quickly so you're ready for the next bump, but you don't want it to oscillate up and down. So you need you need intentional damping. You don't want it to be critically damped. You want it to come quickly to equilibrium, but not so quickly that if the shocks wear out just a little bit, they start oscillating. So you want them near critical damping, at least I imagine, to where they don't take a long, long time. Otherwise, they won't be ready for the next bump. So there's cases when you have a system that you really want to dampen the oscillations. That's fairly common. All right, so that's damping. So there's cases where you have an oscillator where you want to keep it from oscillating. All right, that leaves a really important topic in engineering, at least, and many other fields, called resonance. Okay, resonance. This is an effect that can occur in a simple harmonic system where you can get a really large amplitude of vibration. When you push the system at a frequency it would already naturally vibrate at. I'm going to assign a video online for you to watch that will show this much better than I can show you at a whiteboard like this. But a simple example, if you're pushing someone on a swing, when you push them on a swing, they swing forward, they come back, you push them again, they swing forward, they come back. A swing is a simple pendulum. A pendulum has a natural frequency of oscillation. You naturally push at the same frequency that the swing, the pendulum, would naturally oscillate at if you weren't pushing. So there's a case of a system that has a natural frequency. So here's a pendulum, and if you push on well, that's just a terrible stick figure. If I push on the pendulum at the frequency it wants to oscillate at, I can get larger and larger swings. So resonance is a large amplitude vibration that occurs when a driving frequency, my pushing is called the driving frequency, matches or approximately matches a natural frequency of vibration. So again, this was supposed to be a person pushing a pendulum. So if you push a pendulum, you push at the same frequency it would naturally swing at. A case of this that you'll see in the video would be, suppose you have a building and another building and an earthquake comes. The earthquake vibrates the ground. Buildings have natural frequencies of vibration, a set of them, not just one, but natural frequencies. This might have a natural frequency, one natural frequency, and this another. If the earthquake vibrates at the natural frequency of this building and not this one, it may cause this building to fall, but leave this one. A case where you may have experienced this is some parts of your car might have a natural frequency of vibration, especially if you have an older car. You may find that if you drive at one speed, you may get this real annoying vibration in your car, or this real annoying sound. That's because at that particular speed, the frequency of the wheels turning or some other frequency in your car matches a natural frequency in your car and causes this large amplitude vibration. This is called resonance. Again, the video I assigned will show it better than I can show it at the board. So the way we might show this in a graph would be if we plot the amplitude of the vibration versus the frequency of the vibration that you're pushing with. There'll be also some resonant frequency, F resonant, and you'll get, for most frequencies you push with, you'll get very little amplitude, but when you hit that resonant frequency, this will get really big, and then, but only when you're near that resonant frequency. This happens in musical instruments. We'll see that soon as well. So it's at the resonant frequencies of the musical instruments that you get the notes that you hear in those musical instruments. So this is again termed resonance. It's really super important in engineering. People often try and prevent resonances because they can cause quite a lot of damage in a building structure, for example, or in a mechanical part. All right, so that's all for today, and I will see you soon. Bye.